Hey guys, we are bringing you the second talk from our DemystiCon conference back in April, occurring on the 7th and 8th to coincide with the eclipse. This was actually the first talk from the conference with our dear friend, Dr. Alberto Martinez. He is a historian of science, and he is picking apart some of the very intricate nitty-gritties about where physics perhaps departed from material reality back in the 20th century.
Specifically, he's looking at the fact of Niels Bohr and the corrosive influence that this one person had on the unfolding narratives of physics at the turn of the century. The talk is called When Physics Went Astray, and I think you're really going to enjoy it.
Tell us what you think in the comments. Come over to Discord, come over to Facebook, share the podcast with somebody who you think might enjoy it, and let us know who we might talk to follow up on these ideas.
And if you really like the podcast and you want to show your support, come on over to patreon.com/demystifysci. For a couple dollars a month, you can help us steer the ship. You can help us make sure that we never have to shill pills or tchotchkes or anything else, and are entirely supported by our audience and what you guys are interested in. And there's no minimum that you can donate. So if you have $1 here, $1 there, it would help us tremendously.
So enjoy the conversation and tell us what you think, and we'll see you next time.
The scientific revolution starts now.
The DemystiCon podcast.
Let us see in the dark.
All right, everyone. Well, thank you so much, Anastasia and Michael Shiloh. I'm really happy to be here. As I said, I'm Alberto Martinez. I'm a professor of history of science, history of physics at UTAustin, where I've worked for the past 19 years. Before that, I was at Caltech, at MIT, at several other places. And I look back and I remember that the original reason why I got into history of physics was the kind of topic that I'll talk about today. However, for about 2 decades, I haven't been writing or thinking about it much, but it's time to go back to it. So the question is, why did physics go astray? Many of you know and sense that there's something rotten in the state of physics. And the question is, why? Why did this happen? So I wanted to give you some historical perspective and put some of the blame somewhere. So in 1958, physicist Freeman Dyson, in Scientific American, explained the process by which students undergo when studying quantum mechanics. He wrote, "The student begins by learning the tricks of the trade. Then he begins to worry because he does not understand what he's doing. This stage often lasts 6 months or longer, and it is strenuous and unpleasant. Then, quite unexpectedly, the student says to himself, 'I understand quantum mechanics.' Or rather says to himself, 'I understand now that there isn't anything to be understood.' For each new generation, there is less resistance to be broken down before they feel at home with quantum ideas." So to me, there is always something chilling and disturbing about those words, as if you're trying to break down the students to just take the formula down, just swallow it. Dyson actually accepted the situation, but it annoyed the physicist Alfred Landé, who had contributed to quantum theory. He wrote, "We are not amused, in spite of the fact that Dyson cheerfully confirms the inheritance of acquired characteristics from one generation to another, even such detrimental ones as breaking down to not understanding and yet feeling at home with quantum ideas." Alfred Landé, for instance, he noted the manner in which, soon after the formulation of quantum mechanics, physicists became resigned to having a perfect instrument of calculation, knowing the how and regarding the why as unanswerable, if not as meaningless. In 1983, at a lecture at UCLA, famous physicist American Richard Feynman, he explained to his audience, "Why am I going to sit here all this time when you won't be able to understand what I'm going to say? It is my task to convince you not to turn away just because you don't understand it." You see, my physics students don't understand it either. That is because I don't understand it, nobody does. So when I read those words published in the book, I think this is in book QED, I thought, here it is, here's the evidence. This is an undisputably famous physicist admitting that nobody understands it. If anybody could have gone to the bottom of it, but he says, look, you'll go down the rabbit hole into a tunnel from which nobody has escaped. Not everybody accepted this. Philosopher Karl Popper, here at a young photograph, he said, today physics is in a crisis. It is a crisis of understanding. So my question is, why did this happen? The original proponent of the quark model of matter, Murray Gell-Mann, blamed it on a specific individual. In a lecture, he casually said, the fact that an adequate philosophical presentation of quantum mechanics has been so long delayed is no doubt caused by the fact that Niels Bohr brainwashed a whole generation of theorists into thinking the job was done 50 years ago. So here's the scapegoat. And of course, this is unfashionable. We have all been trained by culture not to do this. When banks took billions of dollars during the financial crisis, naturally commentators and observers said, well, this is nobody's fault. This is something that we all did. You know, we all have to be careful. So when the U.S. invades a foreign country, we talk as if we did it. So culture is relentlessly teaching us never to allocate any blame on any individual, especially if they are at the top of a hierarchy. Instead, we're all supposed to share the blame. So I'm trying to get you to see Bohr as the dark and nefarious guy in the history of 20th century physics. Let's see if I can pull that off. So Bohr used to say, if you're not confused by quantum mechanics, you have not understood it. He accepted that confusion is an important prerequisite to quantum understanding. So Karl Popper, philosopher of physics, he denounced this. He said, so this is, of course, the fundamental point. I mean, the Copenhagen interpretation. For an enormous number of persons, it is ununderstandable. It can only be understood if you're broken in it at school and you don't want to understand. That is the fundamental thing. Don't try to understand. Just take the formula down, but don't try to understand. I think this is a great crime against humanity. Really, I think so. This is the way he criticized it. Consider one of Niels Bohr's early assistants, Henrik, known as Hans Kramers. You all have heard of the Compton effect, light of high frequency scattering off of free electrons loses some of its frequency is reduced. It loses some of its energy. And Arthur Holly Compton, American physicist, famously earned Nobel Prize for this. Now, he discovered it in 1922, but it had been discovered or predicted earlier in 1921 by a student of Paul Ehrenfest, namely Hans Kramers. So he became Bohr's assistant, and he figured out that when a photon bounces off an electron, photon loses some of its energy. In Copenhagen, however, he made the mistake of telling Niels Bohr about it, instead of just publishing it. Niels Bohr hated photons. He absolutely hated the idea that light was really quantized. He couldn't stand the idea of particles, so he badgers Kramers with endless objections. For example, you think about the Bohr model of the atom, you think of the orbiting electron radiating some light. What Bohr envisions coming out of that electron is a sphere, not a particle, a sphere of light. So he's badgering Kramers, objection after objection. Physicist Max Dresden, who wrote a book about Kramers, he wrote, Bohr subjected Kramers to an unrelenting series of interminable and acrimonious discussions in which the photon notion was examined in excruciating detail. When I read excruciating, I think painful detail. Kramers finally capitulated to Bohr's uncompromising onslaught. He took his notes, he threw them away, and he accepted that light is not made of photons, thanks to Niels Bohr. It got so bad that Kramers had to be taken to the hospital. His health broke. But worse than that, Niels Bohr broke his will. He convinced Kramers not to publish, So Kramers didn't publish anything about photon scattering, even though he had the equations. Max Dresden wrote, Kramer's complete reversal is a perfect example of the fanatical adherence recent converts often exhibit to their newfound faith. Again, Max Dresden was a prominent physicist. The wife of Hans Kramers never forgave Niels Bohr just because of the way he dominated Kramers' personality. Kramers' wife, Storm, was a singer with few opportunities in Copenhagen. Kramers' best friend, Romain, ended his friendship with Kramers because of a personality change after Kramers befriended Bohr. Romain hated Niels Bohr. Now, 1924, Werner Heisenberg, on your left, becomes frustrated after hearing a talk by Erwin Schrödinger at a seminar in Munich on what Schrödinger interprets to be the wave nature of quantum mechanics. Heisenberg writes to Bohr complaining, so Bohr invites Erwin Schrödinger to Copenhagen. In mid-September 1926, Erwin Schrödinger visits Niels Bohr, not just in Copenhagen, stays in Bohr's home with his wife, Margrethe, and that is Bohr's wife. Each day, they discuss quantum mechanics from early in the morning, from breakfast until late at night. Schrödinger insists that quantum jumps cannot be real, cannot have something jumping from one place to another without a trajectory or without a wave transmission. Schrödinger wants to know what's really going on inside the atom. They go on and on, hour after hour after hour. Werner Heisenberg joins them for dinner, and he reports that Bohr, normally a pleasant, easygoing conversationalist, was relentless. He kept going on and on like a fanatic. Bohr thought that quantum mechanics was not just a series of discoveries in physics, but philosophical discoveries, that there was something fundamentally wrong with epistemology and ontology, that they were defective, unsustainable, mistaken. This relentless conversation that night at that dinner makes Schrödinger ill. He needs to get away from the dinner table. He goes lie down, and after him goes Niels Bohr, sitting next to him by the bed, while Bohr's wife is trying to get him to stand away. And Heisenberg was just shocked of, how Bohr had become this kind of fanatical personality. So he's with a fever. He drove in physically sick. So Kramers and Schrödinger. Meanwhile, Heisenberg himself is fascinated with a problem analogous to what happened in Copernican physics. So in Copernican physics, of course, what we had to do is overcome our observation. What you see every day is the sun moving. What you see every night is the moon moving. You see it, it's hard not to see it. It's hard to deny it. What Ptolemy's physics describes are the motions of these circles. So when Copernicus comes along, and part of what that revolution consists is, I'm going to teach you not to see that the sun is moving when actually that is what you're seeing. Similarly, Heisenberg's obsession became, how do I succeed in not seeing those paths? A Wilson cloud chamber. You've got a super saturated, super cooled vapor, and you put radioactive substance next to it like uranium, just outside your box where your cloud is contained. And then you see these little paths. As the uranium decomposes, little bits of matter fly through this gas, and they leave these paths. And the paths correspond to the type of particle that's going through it. More sophisticated photograph, in a magnetic field, you see these circular paths. So now, in quantum experimental physics, when you're working with photometers, or really with photomultipliers and various other detectors, even photographic plates, what you detect are little spots, particles. So when you measure the location of particles, what you're detecting is the XY location. And there you have it. It's a little dot. It's always a little dot. And here you have the paths. Now, Heisenberg's problem is that he couldn't understand these paths because they're not accounted for by his matrix mechanics. Matrix mechanics, this was not a function of time, while the Schrödinger wave equation was. So the question is, how do we convince ourselves not to see these paths? Heisenberg is working on this. And he remembers what Einstein told him in a conversation when Heisenberg visited Berlin and they walked to Einstein's house for dinner. Einstein said, a theory determines what you can see. So if you've got a theory in which there are no paths, you should be able to not see these paths. And it occurs to Heisenberg, am I really seeing the paths? Is that what I'm seeing? Because I'm not seeing the particle, how can I be seeing the paths? He realizes what he's actually seeing, of course, is a series of droplets. As the vapor is being ionized, droplets of liquid are formed, and what you're seeing is a series of little droplets. So what you're seeing that looks like a path is actually a series of dots. Aha, no path. We have made the path vanish. And with that breakthrough, that conceptual breakthrough, he moves on to formulate his uncertainty principle. That if you try to measure one thing, the location very precisely, then you lose information or there is no information about the momentum and vice versa. So he's walking around at Violet Park in Copenhagen while Niels Bohr is on vacation in Norway skiing in February 1927, thinking about the uncertainty of the precise location of subatomic particles. And in March 1927, before Niels Bohr returns from his trip, Heisenberg submits his paper. Bohr arrives. Heisenberg tells him, Bohr says, what have you done? Your paper is all wrong. You have to write to them to retract it. You can't talk about subatomic particles as though they're particles when we haven't measured them. You have several descriptions here that are just wrong. And then they get into this heated discussion back and forth. Heisenberg is, I did the paper. There's nothing wrong with the paper. I'm not going to retract the paper. And Bohr's like, you have to retract it. It's wrong. This is all wrong, etc., etc. And they go back and forth until Heisenberg breaks out in tears. How often do you see physicists, adult physicists, crying? This isn't normal. So again, this relentless onslaught of Bohr somehow crushes Heisenberg and gets him to realize, fine, okay, I'll talk about quantum mechanics the way Bohr wants me to talk about it. Never talk about paths. What Bohr wants you to do, in fact, is not just not to talk about paths, but not talk about electrons as having a real existence unless you're talking about an actual experimental measurement. So what Bohr advocates is, of course, that the seemingly contradictory descriptions are just complementary. Instead of a particle being at one place at one time, it's spread out through space like a wave. Why? Because we're not measuring it. And when you try to measure it, then it collapses and shows up at a single spot. So those two contradictory visions, the object is in one place and the object is spreading out through many places, they just can't be accepted if we accept what Einstein called the tranquilizer pill. So you take this little blue tranquilizer pill, known as the principle of complementarity, involves no equations, so Heisenberg's got this inequality relation, Bohr has just some words, and that principle ended up in physics textbooks for quite some time. Now gradually it's been vomited out. Gradually physicists start to realize this isn't really doing anything here, and they've been eliminating it from textbooks. Bohr thought contraria sunt complementa. Descriptions of nature that seem incompatible, contradictory, are not provisional. They are unavoidable and permanent. The seemingly contradictory is actually acceptable and permanent, and is something you should embrace. Just accept it. In 1927, in October in Brussels, at the Solvay Congress, there's a series of arguments in the hotel restaurant, especially at breakfast. Einstein's not giving any talks, he's not talking at the presentations, but at the meal times, he's trying to falsify Heisenberg's uncertainty principle. All you got to do for any one particle, find its x component of location and its x component of momentum. And if you find those in such a way that it transcends the accuracy, the limits of the uncertainty principle, that's it. You've shown that the uncertainty. So it's a nice thing to do. You might as well do it. Einstein's trying to do it, for example, with this hanging metal plate you've read about before. The electron goes through the plate has a single slit, the plate is unmoving, therefore if the electron goes through, then we know the y component of the location of the electron. But if you make the plate narrow enough, then as it goes through the slit, the electron hits the screen and makes it vibrate slightly. And because it does, you can also measure the momentum by how much along the y direction the screen is displaced. Bohr goes away with that, thinking about that. Is that true? Comes back the next day. And this is the flaw. In order for you to read what's on the screen, you've got to shoot light on it. So the stable screen you expected is not stable. It's actually jittering because you're shooting at it with a shower of photons or electromagnetic waves. So there is momentum. There is an uncertainty in the y location of the screen before you even do the measurement. Einstein keeps trying. Einstein criticizing the uncertainty principle. Bohr defending it. October 22, 1930, at the club of the University Foundation in Brussels at Rue de Egmont 11, Einstein presents a thought experiment. Metal box, totally shut. A shutter opens for an instant. One photon flies out. Since E equals mc squared, the photon should be equivalent to an amount of weight. So if this entire box is being weighed, now that one photon exited, we should be able to detect the change in weight of the box. And by detecting the change in weight of the box, you get to measure simultaneously these conjugate variables, the energy of the photon and also the time at which the photon exits the box. Bohr is shocked. Einstein explains this. Bohr has no immediate solution. He's going from physicist to physicist. Einstein is just kind of relaxed and celebrating, puts on his hat, puts on his coat. Somebody describes it, said that Einstein looked like a majestic figure walking out in triumph while Bohr was ambling around like an ape. The next day comes Bohr's triumph. Again, at breakfast, Bohr has the solution using Einstein's theory of general relativity, theory of gravity. Because the box has been displaced minutely by the change in vertical location away from the center of the Earth, therefore, the clock is moving at a slightly different rate. And because it's moving at a slightly different rate, then you cannot avoid Heisenberg's uncertainty relation. Einstein shrugs it off. And in the summer of 1931, Einstein is meeting with Paul Ehrenfest, his good friend, who had become the successor of H.A. Lorentz. And in the discussion with Ehrenfest, Einstein says that Bohr did not falsify the photon in a metal box experiment. Einstein says it's impossible. How can you falsify something that is a machine? And Ehrenfest understood that what Einstein was trying to do was falsify Heisenberg's uncertainty principle. Einstein says that's not what I was trying to do. What I was trying to do is prove to everyone, because Ehrenfest had been there, prove to everyone that certain quantities have values before we measure them. In other words, the photon escapes and we haven't measured it. We haven't done anything to measure its mass, its energy, its momentum. We haven't done anything to try to interact with that photon. We haven't done anything. Yet by measuring the change in weight of the box, we're able to know something about a particle that is traveling away from the box at the speed of light. Ehrenfest is shocked and annoyed because to him, Einstein is changing. What happened? What happened was Einstein was trying to falsify the uncertainty principle. Now he talks about a box that was showing that basically there are these hidden variables as we get to know them. That's in 1931. Einstein allegedly trying to prove that a photon has a value before we measure it, before we interact with the photon. It has a value. 2 years later, Ehrenfest is in Amsterdam, returning from a conference in Copenhagen, one of these Bohr conferences. Ehrenfest goes to the university to say hello to some friends. He visits his lover, Nellie, with whom he had been having a relationship, an extramarital relationship that he had pledged to his wife would not continue. Then he visits his disabled son, Wasik, at the Institute for Afflicted Children. There, Ehrenfest pulls out a gun, shoots Wasik in the face, and then kills himself.
Oh.
Ehrenfest had left unmailed letters to some of his friends, including Einstein and Schrödinger. Now, Ehrenfest had had an emotional breakdown at Niels Bohr's house. As he's about to leave the conference, he runs into Paul Dirac. And Paul Dirac sees Ehrenfest extremely upset and distraught. And basically, Ehrenfest confesses that he doesn't understand physics anymore, that he can't take it, that he cannot keep pretending, that he's exhausted. And he thanks Dirac for saying nice things about him, but he says that he doesn't deserve that kind of praise. Ehrenfest had left these unmailed letters to individuals such as Albert Einstein and Niels Bohr, in which he wrote, "In recent years, it has become increasingly difficult for me to understand new things in physics. I tried and struggled until I became a nervous wreck. Finally, I gave up in despair. It made me lose all interest in being alive." So again, on the one hand, you've got this tranquilizer pill telling you accept it, stop asking questions, just take the formula down, plug and chug, plug and chug, plug and chug. Don't think about it. So in hindsight, part of what's happening is Niels Bohr tried to formulate a model of the atom with orbitals. It didn't work. Because it didn't work, he becomes convinced that it cannot be done. Whenever somebody tries to do a trajectory, such as a trajectory of photons or whatnot, he doesn't want the trajectory. So Niels Bohr, who we associate as someone who was creating images for physics, becomes the opposite. He becomes the kind of person that doesn't want you to do an image and doesn't want you to change the fundamental concepts of classical physics. In other words, once quantum phenomena have arrived, and once we've discovered that the classical concepts are wrong, then Niels Bohr steps in and says, but don't change them. Use them only whenever they work, and if you use them delicately, you will find out that really there are no contradictions. At the time, the early 1930s, both Bohr and Heisenberg thought that the job of physics was nearly done. Heisenberg thought they had a complete theory of the atom. They had the fundamental entities of matter, one negatively charged, the electron, one positively charged, the proton. They still thought back then that perhaps neutrons were just a combination of protons and electrons in a particular arrangement, making up all kinds of atoms. By 1934, Karl Popper had met Werner Heisenberg, and he recalls that Heisenberg gave him this description of the situation. When I met Heisenberg during the winter of 1934 to 35, as I already told you, he did believe that his indeterminacy relations mean that we reach the end of physics. He thought those relations mean that we cannot penetrate any step further. And he remained believing it all his life. But we did penetrate, says Karl Popper. Talking about Niels Bohr, Karl Popper wrote, Bohr thought we had reached the limit to which our understanding could penetrate. It was the end of the road. I skipped some words, and an act of renunciation of our understanding was needed. In other words, Popper picked up on a word that Niels Bohr used again and again, renunciation. Niels Bohr said, we must renounce the efforts to understand subatomic phenomena in terms of space-time diagrams. In other words, don't do it and don't try to do it. We must renounce the efforts to describe quantum mechanics in terms of images and pictures. We must renounce the effort to come up with causal explanations of quantum mechanics. We must renounce the efforts to change the language of quantum mechanics. So this series of renunciations, almost as if there's some sort of a religious orthodoxy, a series of things you have to stop yourself from doing, If you stop yourself from doing, then you can live at home with quantum mechanics. Similarly, Werner Heisenberg thought that quarks would never be found. In other words, that they would never be discovered as actual things in physics. He thought they were theoretical inventions. Of course, he was wrong. Similarly, when Richard Feynman presented his Feynman diagrams, these chicken wire diagrams about the paths of particles that we have not seen or measured, Niels Bohr was at one of those early talks. And Niels Bohr stood up from the audience and said, this is all wrong, because we already know from quantum mechanics, which teaches us that particles do not have paths before we measure them. So again, Niels Bohr is wrong about Feynman diagrams. Heisenberg was wrong about quarks. And there you see the progress happening, Feynman's progress happening precisely by disobeying the kind of thing that Niels Bohr wanted to be done. Heisenberg wrote, "We cannot and should not try to replace the concepts of classical mechanics by any others. Keep in mind the limited range of applicability of the classical concepts while using them, but we cannot and should not try to improve them." So again, you see the shaping of this orthodoxy by Bohr caught this number one advocate, this apostle, Heisenberg, who then they both go around country after country saying, take the formula down and accept the mystery. Language became ambiguous, confusion became common. Heisenberg said, the concept of complementarity has encouraged physicists to use an ambiguous language, to use classical concepts in a somewhat vague manner in conformity with the principle of uncertainty. When this vague and unsystematic language leads into difficulty, the physicist has to withdraw into the mathematical scheme and its unambiguous correlation with experiment. Niels Bohr remained confident that the principle of complementarity exhausted, in his words, all conceivable knowledge about the visualizable nature of atomic phenomena. That's it. You want to visualize subatomic phenomena? Just read Bohr's principle of complementarity. Stop working on models, causes, space-time diagrams, or finding new subatomic particles. All you got to do is just take this down. Again, a more detailed space-time coordination of atomic events was impossible. In principle, thought Bohr. Acclaimed physicist John Bell openly admitted, for myself, I never got the hang of complementarity, and I remain unhappy about contradictions. Well-known physicist David Bohm, who proposed an alternative interpretation of quantum mechanics, he rejected Bohr's view, and he described the situation as follows. While most physicists claim to subscribe to Bohr's position, they do not always realize its full implications. For example, many physicists, if asked whether the electron exists in some fundamental sense, would answer yes. However, Bohr himself had emphasized that there is no meaning in talking about the existence of the electron except as an aspect of the unanalyzable pattern of phenomena in which its observation takes place. In other words, there's an experimental setup and interaction between the observer and this system, and you cannot analyze this further. The electron is part of that thing. It's not something that just exists in itself. To clarify, Niels Bohr did not, to the contrary of some misrepresentations, think that the observer or your consciousness has an important part in quantum mechanics. He thought these things have no significant role in the interpretation of quantum mechanics, but the interaction between the measurement apparatus and what is being measured. So following Bohr's renunciations, attempts to do these causal space-time diagrams, images, explanations became unfashionable. The respect for Niels Bohr authority is illustrated cutely in an anecdote by another one of his students, H.B.G. Casimir. He wrote a poem in a recollection by Bohr. He had been discussing with his students, why is it that the good guy in American cowboy western movies always wins when he actually shoots second? And then Bohr argued that maybe by shooting in a defensive manner, you're actually a little bit quicker than the other guy who's doing it. They didn't believe it. They set it up. They pulled out their guns. And indeed, even though Bohr was the good guy, he always managed to pull his gun faster than the others. So Casimir wrote, "This tale has a moral, but we knew it before. It's foolish to question the wisdom of Bohr." Casimir repeated, "The moral that one should not doubt Bohr's wisdom." Inspired by David Bohm's pilot wave explanation or interpretation of quantum mechanics, Louis de Broglie regained interest in physics after 40 years. Louis de Broglie had formulated the idea even larger subatomic things are associated with waves. And he was so impressed that he was able to break the spell of Niels Bohr that he said, "It took me 40 years to regain my mental independence." He lived a long time. He was able to outlast the spell. So in the end, what can I say in closing? Come up with pictures, come up with models, causal explanations, hidden variables. I think that's where the future lies. I think that's where the progress is. I think it's unfortunate that physicists embraced this kind of level of needless abstraction in their explanations. I do think that this was caused mainly by this one character, Niels Bohr. Einstein became convinced that Niels Bohr is someone who just doesn't listen. Heinz Reichenbach had a similar experience. He met with Einstein, had a very pleasant conversation. But then when he tried to meet with Niels Bohr just wouldn't let him talk. And Reichenbach's wife writes that it was very crushing for this young scholar, this philosophy of physics, that this famous physicist wouldn't let him put in a word. All right, so I thank you with that. I leave you with that. Thank you all so much.
Thank you.
Thank you.
All right, so what we're going to do is we'll take some questions from the audience and from the live stream, and then Anastasia and I will also try to start a little conversation here.
Tom brings up my book, Negative Math, in which I discussed debates that had lasted a few hundred years on the nature of negative and imaginary numbers, and eventually complex numbers and hypercomplex numbers. And there we see in mathematics and algebra a similar rise of abstraction and a similar pushback by people who wanted mathematics to have physical meaning and especially geometric meaning. At first, certain things like imaginary numbers and complex numbers did not, and there were paradoxes in what could be done and what couldn't be done. So I think Tom is asking me whether this is a similar process, and I would say absolutely. I would say that to some extent, transformations that happen with relativity, quantum mechanics, and modern physics in particular are emulating and echoing ways of talking and also ways of unthinking that have become fashionable in mathematics. In other words, let the formalism think for you. You don't have to have a mental picture. Don't try to convert it into words. The algebra does not have to match any diagram. Those kinds of transformations happen in mathematics first, and then later they become emulated by these physicists who had, of course, imbibed that way of talking when studying mathematics. So, again, I think it's unfortunate. You look at something like the imaginary number I in equations of modern physics, and then you look at the history of negative and imaginary numbers, the history could have gone in other directions. There could be other ways to represent I, and there are other ways to think of I other than perpendicularity or rotation. So by having the most usual interpretation, which is nothing, just don't think about it, or by having the most common ones, perpendicularity or rotation, physicists miss out on the fact that this is just an algebraic structure that should be analyzed in terms of the particular physical phenomena that's being discussed, rather than allowed to exist as though somehow the physics is obeying this these squiggles of ink. The squiggles of ink are at best should be descriptive in physics, but I think it became common to enable a sort of a black box interpretation of mathematics, where in matrix mechanics, for example, you have the input that's got to do with something that is intelligible, you have an output that might have to do with something like the amplitude of some light wave, and then you're able to kind of, what happens in between, it's unclear. So, yeah, thank you for bringing up my book, Negative Math. I'm glad that you've looked at it. But yeah, both of these projects for me come out of a frustration. In other words, what fascinated me about physics was that something went wrong with it. I thought somebody should try to work on the interpretation and understanding or reformulation of quantum mechanics. But by the time I got into physics and history of physics, that sort of stuff was at some level forbidden. And so why is it that I mean, because that's the unusual thing, that physicists will literally get angry about this. They're going to get agitated and angry. Why are they having that reaction? If they know a ton of physics and someone else doesn't, when that someone else, Joe Schmo, asked them a question, why do they get so angry about it? And so there's something irrational happening here. And I think it's caused by this philosophy of quantum mechanics that Niels Bohr formulated.
If there was an alternate history, I don't know if anybody believes in dimensions and that sort of thing, but in which Niels Bohr was a regular mechanic instead of a quantum mechanic, how would physics be different today? That was my question.
I like that a lot. Well done.
There's one way to reformulate that a bit. Thank you. His question is, if we were in an alternative reality in which Niels Bohr were just a regular mechanic rather than quantum mechanics, how would the world be now? I think particle concepts, especially the particle concepts of light, would have received less resistance. For example, the Compton effect would have been published and discovered earlier. Talked about electrons necessarily emitting spheres of light rather than emitting single photons would have evaporated more quickly. I think Heisenberg, by his nature, would have gone more towards the particle interpretation of subatomic phenomena. So on the one hand, you had wave picture, people such as Schrödinger, Einstein, and quietly supporting them, Max Planck, and numerous others. And then on the wave particle side, you have Bohr, Schrödinger, Heisenberg, and Pauli, a series of others, especially the younger ones. But you don't actually have someone representing the particles. So to me, it's kind of interesting that it's an asymmetric discussion, and that someone such as Paul Ehrenfest is caught in the middle. And the reason Paul Ehrenfest is in it is partly because his friend Walter Ritz had died. So Walter Ritz was the guy at Einstein's college where he studied physics and math, who was viewed as a genius. So that guy was coming up with an alternative theory, an alternative relativity theory, and he thought that Maxwell's equations were wrong, and he thought that this stuff had to be replaced seriously. That guy dies, and then Ehrenfest, who never felt that, he felt he was like the Barney Rubble to Walter Ritz's Fred Flintstone. To give you an example, Hermann Minkowski talked about Albert Einstein as being a lazy dog. He said, I never thought Einstein could do something like this. And he talked about Walter Ritz as being a genius. So the genius dies, and then we have this situation in which Paul Ehrenfest and others have to cobble together what to do. I think it's a great thought experiment to think, because it's a way to measure how one person's influence affects physics. And I'll give one more dimension. Compare Bohr's style, which is to invite every bright, prominent physicist to spend time with him, not just in Copenhagen, but in his home. Compare that to Einstein's attitude, which is leave me alone. I just want some time to work on my stuff. I'm not trying to build a school. The Einstein School of Physics, he could have one assistant or two assistants, but that's it. It's not like he's trying to organize the annual Einstein conference at Princeton. He's not doing that. So I think Einstein's attitude of being standoffish and Bohr's attitude at wanting to take center stage and create a hierarchy, a community of physicists. It's not all bad. He was a nice guy. He was deeply beloved by many people, deeply shaped the way we misunderstand quantum mechanics. So people like to talk about understanding quantum mechanics. I think there is no understanding. It's a misunderstanding. And then there's just different degrees of it, and different degrees of how comfortable people are with their confusion.
Yes, Joe Olson. Are you familiar with an article that was published in Physical Letters in 1996 by Robert Ashworth called The Helical Travel of Light, in which he set up waveguides and he was able to prove that light is a photon moving at 1.7 times the speed of light, and that the wave is generated from that, moves in a helical pattern away from where the particle's moving. And the analogy that he uses is if you have a boat that's going down a lake, the boat is moving at a certain speed, but it generates a wavefront, and as the wavefront hits the beach, it's moving at a lot less velocity than the boat is. And so that solves the duality problem of particle or wave by making it particle and wave, and we're only observing a portion of what's actually happening.
Joe, I haven't read that article. You said that the photon itself is moving at 1.7?
Right.
And how does he explain why physicists still measure that kind of speed? Does he?
Yes, he does. He shows you exactly how he sets up the waveguides. He shows how he was able to measure the speed of the photon and then also separate that, and he uses the mathematical series. I think it's the square root of 3. The bottom line is by describing the helical pattern, he's able to describe what the velocity was.
Yeah, I haven't seen the paper, but I'd be happy to read it.
Oh, I'd be happy.
And I, you know, this is one of those things. The speed of light. It's one of those things that somehow something psychological happens with physicists and scientists in general. They like having restrictions and walls. It's somehow very soothing to the great many people to think light speed has a limit, and that spin limit is a fundamental law. It's like, here are the 10 commandments, and this is one of them. You know, I've met Nobel laureates who have thought that the speed of light, Ken Wilson, for example, Nobel laureate, he thought that maybe the speed of light is changing over the decades and the centuries. In other words, that Einstein formulates the special theory of relativity. The speed of light is maximal velocity constant, as Henri Poincaré had predicted. Poincaré had said we should formulate a physics in which the speed of light is a limit. It's nice and pretty, but once you formulate the general theory of relativity, Einstein had to abandon. He had to abandon the principle of the constancy of the speed of light. That was abandoned. So it's interesting how simultaneously we imagine, well, yeah, but in an inertial system, it's constant. Yeah, but this is the problem, ladies and gentlemen. The problem is there are no inertial systems. Einstein alone understands that's a serious problem. In other words, Einstein understands when he formulates the special theory of relativity, he's trying to get rid of a privileged frame of reference, the ether, but then he realized that he has replaced it with an infinity of privileged reference frames called the inertial systems. But when you look at a train moving in a straight line, the train is traveling on planet Earth, and planet Earth is spinning. So the train is not moving in a straight line. And when you shoot a space capsule, it's not moving in a straight line either. Neither is the moon, neither is any asteroid or meteorite or planet that has ever been observed. So in fact, inertial systems are fictions. So it's strange to say, well, the speed of light is constant in inertial systems. Yeah, but we haven't found one. We haven't found one. So I'm not offended if somebody, 1.1 or 1.7, whatever, the normal one was to talk about, well, a photon is traveling in that direction at c, photon is traveling in that direction at negative c. What is the rate of separation of two photons? A normal person would expect that it is twice the speed of light. But then why don't they say that? Well, because if you put those two variables into the addition transformation formula for velocities, you find that one photon is receding from the other at the speed of light. Sure, but that's from the perspective of the one photon, not from the perspective of the center. From a third reference frame, they're both separating from each other at twice the speed of light, which is a different kind of velocity. In other words, there are different kinds of velocities. Some of them are relative to yourself. Others are relative to an object that you are measuring. But yeah, I don't know. I have never heard of this. But just to give one more detail to the point that was brought up by Joe, was it? Yeah. In the case of polarization, for certain kinds of polarization, there is this discussion of the electromagnetic wave moving as a spiral. So these kinds of, I'm not annoyed. I'm not annoyed if somebody says something or writes something. Hopefully they're right. I haven't looked at it. I don't see why people get angry at these things, but that's just how it is. It's an orthodoxy. And I think subconsciously what happened was physicists and mathematicians didn't realize that by having emulated traditional styles of learning, they were copying medieval, obsolete ways of teaching from Catholic curricula in which you were teaching from authority. Look, this is the catechism. Take it down and accept it. You cannot bend any of it. And if you bend any of it, I'm going to get angry with you. I'm going to excommunicate you and I'm not going to talk to you because you are so wrong. You're not even wrong. And they have so many devices for shrugging off people and disrespecting them. It's just not a healthy attitude for physics. I don't understand it. If they get an email, they don't want to reply from someone who they think is a crank, then don't answer. Don't get angry about it. But anyway, it's uncivil and it's too bad. And hopefully physicists will find some way to move away from this way of shutting down discussions.
Can I ask you something more personal? In your own journey as a physicist, what drew you into these questions? Was it encountering that kind of resistance, that almost ecclesiastical hierarchy, or what brought you into the fold of realizing that there was something wrong here?
Well, first of all, I'm not a physicist. I'm a historian of physics. So yeah, I studied physics, but the way to rephrase Michael Shiloh's question is, what drew me out of it? What drew me out of it was this resistance. I mean, in other words, you go to a course on quantum mechanics, they talk about the wave-particle duality for half an hour or for 20 minutes, the two-slit experiment. If you're really curious about it, you quickly find out this is not the place where I'm going to find any discussion. We're just racing through equations, applying them, and yeah, I can do the equations. You take the formula down, you solve the thing, you gave the answer they wanted you to give them, but you don't understand. And then it's sad that then the physics structure is driving out people who say, look, I want to understand what the hell an electromagnetic wave is. I don't get it yet. It's driving them away. So I do agree with Bohr with Karl Popper, that this is a crime against humanity. There's something wrong here because many thoughtful people are being driven out of physics. So that's what drove me to history of physics. Because I thought, at least if I read Feynman or Einstein or Bohr, I have a chance at understanding something, but not in a physics course where a professor has 0 time and 0 patience for explaining some of this stuff. They just want to rattle off some things so they can go back to whatever else they were doing.
Well, they might not know themselves.
I'm sorry?
They might not know themselves.
They might not know themselves, yeah. So when Heinrich Hertz wrote his Principles of Mechanics in the early 1890s, he said that he noticed that physicists, when they're teaching the foundations of mechanics, are impatient. Like they want to get away from it as quickly as possible to get to the application. And I think something like that is happening too. But, I don't know. I think it's interesting that now, because of the internet, people can meet each other and communicate. And I'm glad that Michael Shiloh and Anastasia are working on atomic material models of whatever the hell is going on. Because it's a constructive, positive activity. There's nothing wrong in trying to visualize the invisible. People have been doing it for hundreds or thousands of years, and they've been very successful at it. Major breakthroughs come from it, and even being wrong can be useful. So I think it's exciting stuff. I think that it's too bad that physicists think everything is done and that all they need is a theory. Not physicists, some physicists think that everything is nearly done and that they just need their theory of everything to wrap it up. It's not done. We don't understand what's happening. I sure don't.
Do we have any more audience questions? Okay, we have tons. All right, let's do that.
Can I get you, do you need anything to drink or?
Some water.
Some water? All right, I got you.
Hello, Gary Barham from the Netherlands.
Gary,
put that thing right up on your mouth. Thank you.
Alberto, could you say something more about your idea of negative numbers and how that relates to the Dirac equation, which threw up positive and negative solutions to the one equation, and how that relates to antimatter, which we're not really hearing enough about at the moment?
Sure. I don't have much to say about antimatter. The asymmetry between antimatter and ordinary matter is fascinating, of course. Some of these names are ridiculous and are accidental. The idea that an electron, in other words, at some point somebody has to go into this, and I'm sure Michael and Anastasia are helping in the process. I want to get into a process myself, which is what are the proper labels for these things? If you have a battery and you don't know what the hell it's doing, then you say, okay, well, let me call the side's positive and the other one's negative. It's just a staple of one's ignorance. And then later, physicists discovered, after they had called something negative, that the electrons were there, that the things were there. So it's absurd that we begin thinking about electricity by thinking that charges are negative. That's an absurdity. That's not what's happening. And then thinking that therefore electrons are negative. Electrons are just particles of electricity. You don't need to use the word negative. And then it's doubly ironic that then when you find one that is positive, then they call it a positron, which is fine. Oh, it's okay, but then they call it antimatter. That's what weird. Makes it sound like it's something far more mystical. Look, what I can say about negative numbers and imaginary numbers and the like, which you can see in a couple of my books, is that, as people complained early on, there really are certain asymmetries here. In other words, if going to the right is positive and going to the left is negative, then why does positive times positive keep you on the right, but negative times negative take you to the right? So these things, the reason they're explained is by abandoning that analogy, by teaching the student negative is going to the left, except when we're talking about negative times negative. Then it doesn't make any sense. Then they change the meaning and decide that one of the two negatives means change direction. It didn't mean that, but in order to make it work, then they say, it actually means change direction. And then because of these kinds of things, this asymmetry in which both negative 2 squared and positive 2 squared give you positive 4, because of that, then they came up with this paradox, no square roots of negative numbers. And because of that, then they invented these numbers called square roots of negative numbers. But in other words, as I showed in my book, which was published by Princeton University Press in 2005, you can formulate a consistent algebra in which minus times minus is minus. And if you do, then there are no imaginary numbers. How would a physics based on negative times negative equals negative, what would it look like? It's up for grabs. Why isn't it something people do? Because they were taught not to do that. In other words, the ancient pyramid of the science, or the hierarchy of the sciences, in which math is believed to be independent of physics, that hierarchy still dominates. The physicists still believe that they can't bend the rules of math, when in fact they have. Electrical engineer Oliver Heaviside, unsatisfied with the complexity of Maxwell's 33 Cartesian equations, unsatisfied with the coordinate algebra that we know that we call Cartesian geometry, unsatisfied with that, said, look, let me use Hamilton's quaternions. And then unsatisfied with Hamilton's quaternions, because the square of every vector in Hamilton's quaternions is negative. If kinetic energy is equal to 1/2 mv squared, and v as a velocity is a vector, why is kinetic energy always negative? If v is a vector, and in Hamilton's quaternions all vectors are imaginary components, why is kinetic energy so Oliver Heaviside decided, I have to change the sign of the squaring of vectors so that it's positive. And in doing that, he creates this new math called vector algebra. In other words, physicists have changed mathematics. Once in a while, they just, okay, I'll design a new kind of math. So I do think that an important problem is when you're using a mathematics that was not designed for the physical problem at hand, then there's a mismatch, and you have to do things like ignore the complex roots. Oh, it's got a bunch of complex roots that are meaningless, so I'm going to ignore them. In other cases, you're blessed because the math, in the case of Dirac, you discover something like the positron, and you're able to discover something cool. But no, I think it's a fascinating topic, and I do think that there's something questionable whenever you see the square root, and negatives in physics. Think about the fact that they're getting it from this asymmetrical algebra, which is this historical product that they get from Descartes and others that wasn't designed for certain things, like the analysis of motion in space. It wasn't designed for that. That's not what it was designed for. Then they make it work by, doing all kinds of tricks and but it's I don't know. It's not. I think physicists should look at math as an instrument that is modifiable, and that they should take part in shaping and commenting on.
All right.
All right, Wayne. So I think what we'll do is we'll finish out the audience questions, and then maybe we'll take a little break if anybody wants to use the restroom, and then Anastasia and I will have a little conversation with you to finish out the session.
Sure. Thank you.
Thank you so much. Very interesting presentation. My question is, given the history that you've seen of physics and the educational system that has evolved from that, what do you see as a good model for going forward for better understanding physics and getting a broader and more maybe not cohesive, but a more comprehensive view of all these topics? So the future of education is a short question.
Sure. So I'd say a couple of things. The first one, physics education should not begin with the algebraic equations. There are these famous physics lectures online, MIT professor Walter Lewin. And this stuff at one level is great, but at another level, what you'll see, what the guy is actually doing is trying to convince you that the equations work. So he gives you the equation first, at 20, 30 minutes, and at the end, then you have some slight demonstration so that you can see that he's right. I think that's a wrong way to teach physics. You should begin with the experiment, for example, double refraction, polarization, Ørsted's experiments. You should actually see what's happening, Faraday's experiments, and after you see them and you start describing them, then you should start introducing the equations. So I think that's very important, because otherwise there's a kind of deception. Students barely know what's really happening because they get a complicated math that leads to a simple experiment, and then they think that the simple experiment has proven the complicated math, which is not it. The complicated math was formulated painstakingly to explain a series of experiments, including that simple experiment. Many things are missing if you don't get to actually play around with the object. So that's one thing. The other thing is the physics of materials. We now know a hell of a lot about glass and fibers and materials that are involved in physics experiments. So we shouldn't teach these things as though they are 19th century drawings. You take a surface that is not flat and you represent it with a simple line. And you take spaces that are not empty and you represent them as emptiness. And then you say things like the word vacuum, and then you give the fake idea that the space is empty. It's not empty. It's seething full of stuff. Electromagnetic radiations, photons, mu mesons, neutrinos, leptons, all kinds of stuff. So you should talk about it in a way of what we have found rather than creating these cartoonish ideas, because part of the drama comes from those cartoons. It's those cartoons and only those cartoons that say it interfered with itself because there was nothing else there to interfere with. It's ridiculous. An electron biprism is not emptiness. The Tonomura experiments of 1989, you're allegedly getting single electrons to interfere by shooting them on either sides of a wire that's running electrical current through it. Well, guess what? This thing is full of photons. So you should welcome the possibility of interacting what the photons are doing with the electron, rather than, again, treating it as though it's empty space. So there's this habit of using these absurd cartoons that should have been superseded, and they don't supersede them because people are not trying to do models, and the habit of ignoring substances. For example, when you talk about, I don't know, what a wire is like, when you transmit a current and you're talking about the field, what the hell is the wire? What is the substance that is around it? What is the air and the water that is around it? All that sort of stuff has to be brought into account. Otherwise, the whole thing seems more mysterious than it actually is. And, there's a couple of thoughts. But again, I do like models. I like causal explanations. I think teaching students that models and causal explanations work and have worked for thousands of years is important before we even contemplate not using them. I think if And whenever someone fails, they should say, look, I haven't found a way to do it, rather than saying it can't be done. Because again, that attitude that something is impossible is just, it's so often wrong. And when you look at the history, it's just a wreckage of moments when someone said something is impossible. All that happened is they couldn't do it.
Yes, I want to unpack that some more after we come back to it. I want to talk about the future very much. But
Any more
audience? Yeah. Yes.
All right, we got a couple.
We got two. Go ahead.
I am an engineer, so I take a kind of hammer mechanic approach to these things. But the bidirectionality of time, perhaps at the below quanta level, which is suggested perhaps by Susskind's fractal notion of time, and then the Aronov-Bohm effect. He does his bidirectional vectors. I haven't read your book yet, unfortunately. I'm just unpacking that now. But does that suggest perhaps that Bohm has a tiny little possibility of defense in his extreme requirement for the entirety of the experimental apparatus to produce the result, in the sense that it is the entirety of the apparatus present, which kind of suggests that CERN might be the philosophical equivalent of counting the number of angels on the head of a pin?
Which suggests that that CERN is what?
CERN might be the modern analogy to philosophers counting the number of angels on the head of a pin.
So you're suggesting that the experimental apparatus is so important to the experiment itself that you're measuring the apparatus rather than something else?
Yeah, and it's getting like epicycle upon epicycle upon epicycle.
You've just built such a complex machine that the thing that you're getting out of it is just this product of layers and layers and layers of
epicycles. But it's the quanta of time that might enable Bohm not to be entirely wrong. He wasn't a dumb man. He was just a stubborn man.
Not entirely wrong in terms of?
It seems that he was extremely adherent to the physicality of the setup producing the result.
Yeah, I mean, I think that the question is it possible that the experimental results that we are getting from these massive experiments are simply the product of the design of the machine rather than measuring something meaningful? Is that the...
Yeah.
Okay. It's a good question.
Thank you. I appreciate that you're an engineer. I do think that engineers and experimental physicists somehow don't get the same appreciation as the theoretical ones. I just don't know about that particular experiment and about the quantum of time that you're talking about. I'll say this. Look, I don't work on this more recent cutting edge stuff, so I just don't know the answer. But I'm sure there are other people here that can discuss this topic with you. I just don't know about this stuff. I think of me as someone who has looked deeply into more obsolete history of physics than more recent stuff. I do think it's quite reasonable that they're measuring the apparatus, that the phenomena are artifacts of things that they are not taking into account. But again, this is just a superficial, from what you've heard and maybe vague things I hear. Go to David Bohm's interpretation of quantum mechanics. He envisions this kind of pilot wave telling the electron where to go. And Einstein thought that Bohm was trying to get his results cheap, that this was too simplistic. Bohm felt a little bit bad that his way of getting at hidden variables was just adding variables. That it would seem to be impossible that there can be hidden variables. Bohm showed to be trivially true. You can add variables all you want, so long as they don't make any difference to the variables that you have. So I'd be fine with finding out that some version of Bohm's model is correct. I don't have an intellectual problem with that. I have a bigger problem with everything being waves and particles that are in one spot interfering with themselves as if they're in multiple spots. So there are things that intuitively bother me, but Bohm's model is not one of them. So if you say, oh, well, maybe this and that can happen, the fractal nature of time, and that might lead to Bohr's model being correct. I'm like, that's fine by me. I don't mind. But thank you. And we had one more back there.
I was wondering if you could sort of speak to how do you think that the larger history of, events of the 20th century might have played into the way that the history of physics progressed, and maybe the zeitgeist or whatever it is, the world wars or the, rise of communism and that sort of thing?
Boy, yes. The first part, I was going to say that's an essential and necessary question. But then when you brought it to communism and world war, but let me start from the first part. And let's see if we're on track here. I do think that what happened in physics is a byproduct of what was happening in other fields. And what was happening in other fields is they didn't want to be dominated by physics. This is the key thing. They wanted to get away from this hierarchy in which biology depends on physics and engineering depends on physics and everything depends on. They wanted to get rid of that. And along comes Einstein and says things that seem to mean that everything is relative. Of course, that's not what Einstein meant. And Heisenberg, things are uncertain and there are things we can never know. And Bohr, and things are contradictory and the contradictions are unavoidable. Those things were enormously rewarding and embraced by intellectuals in Europe and worldwide who were seeking to escape from the rigid determinism, but above all, the intellectual supremacy of physics. So they could turn and say, aha, so you physicists don't know what the hell you're doing. Aha, so you physicists are a bunch of confusing nonsense too. Aha, so you physicists are just a bundle of contradictions, right? Aha, so you have no cause and you can't find the cause. So it was enormously liberating in the humanities and the social sciences to finally have a way to transcend the belief that people should imitate physics. And instead it seemed that physicists, having found this uncertainty and indeterminacy, then sought shelter in mysticism. And whether it was Eastern or religious, in other words, that, if anyone is uncomfortable with a miracle can be that Pythagoras was seen at two cities at once, or that Jesus turned a stone into bread. If you're uncomfortable with a miracle, then physicists said, well, the biggest miracle of all times is every single billionth of a second, the entire universe is fragmenting into indefinitely many copies of itself. Yeah, I mean, what's a bigger miracle? One stone into one loaf of bread, or the entire universe being duplicated? Trillions of times every second, just so that the Schrödinger wave equation can be correct. Just so that physicists don't have to own up to the fact that the Schrödinger wave equation is obviously an incomplete account of the physics. Just for that, they need to create these endless duplicates. So there's a rise in mysticism, in pseudoscience, and in the peripheries of physics that happened because of these transformations that Bohr and Heisenberg innocently shepherded in. That's not what they wanted, but this is what happened. And moving to politics, I don't know. You said communism, and what else did you say?
World wars.
Well, I think that the division between those that took the ether to be the case and so there was a division between those who believed in the ether and those who believed in general relativity. And I think that it was strongly swayed during World War II that the Nazis called relativity the Jewish science. And I think that it's impossible to escape that political dimension of subsequent adoption, because how can you accept the theory that the Nazis are walking around and saying is better than the Jewish science? Like, it just, I think that everything that we see in the way that people behave seems to imply that they will choose the theory that aligns with their moral values. And so you can't divorce it from the politics of the time.
You got to keep in mind, like Lorentz had an equivalent relativistic theory that did involve mediators and kept the ether intact, but it was passed over. And as far as I can tell, it's empirically consistent as much as relativity, but we're stuck with the mediatorless one as a result of that.
Let me take a stab similarly along the lines of what you guys are saying. After World War I, the German industrial scientific military program was crushed. They thought they would win. They didn't understand why they were defeated. Their armies were not defeated, and suddenly it was announced that they lost. So historian Paul Foreman, formerly at the Smithsonian, has analyzed and argued that this psychological crushing of the German intellectual, mathematical, physical program, which is their physics and math would lead them to industrial and military success, that crushing led the German people to seek a different Lebensphilosophy, a different philosophy of life that would embrace non-deterministic, acausal, pseudo-mystical components that were traditionally obtained through mysticism and whatnot. And once the culture wanted it, then the physicists provided it. In other words, the culture wanted first lashed back against this deterministic inhuman physics, and then the culture, the physics created an uncertain quantum mechanics so that people could have that. Now, it's fashionable in the early part of the 20th century for Einstein, Heisenberg, and others to pat themselves in the back whenever they seem to go beyond the bounds of common sense. So 1 meter ruler is no longer 1 meter long, and it might be 1 meter long for me, but for someone on the train, it's actually shorter, and that's not contradictory. It's okay because these are two separate images of something that go together. Or Bohr comes along and says, hey, you have an apparent contradiction, but that's okay because that intellectual program of moving away from common sense and mechanical models at some level was sympathetic to certain anti-rational elements. And so then when Max Planck is meeting with Hitler in World War, before the start of World War II, trying to convince Hitler that some Jewish people are good, and Hitler is just yelling at the guy, Max Planck gradually discovers that his worldview has been betrayed, that there's no way to reason with these crazy people. There's no way to stop the avalanche of irrationality and thoughtlessness that has happened. Interestingly, the Nazis side with these retrograde or reactionary physicists who wanted to get rid of modern physics, which was crazy and wrong. I do think that was, of course, crazy and wrong. And they were doing book burnings and burning books by Einstein and others. And they were accusing Heisenberg of being a white Jew. So at some point, these philosophical and physical theories do get taken up by society as society goes increasingly militaristic and insane. But I can't, of course, blame Bohr or Heisenberg or any of those guys for contributing somehow to some of these collapses, such as happens to Jewish physicists in World War II. The alternative is people such as Heisenberg should have, and Planck, made some stronger defense of Jewish physicists. They should have, and they didn't. Instead, Planck was signing off orders to have physicists dismissed, and Heisenberg was helping them be shuttled to Copenhagen so that Bohr could try to get them jobs. So it's all very tragic. But in terms of the zeitgeist of the 20th century, I do think there's something unfortunate that happened with the loss of visualizability and the laws of causal thinking in quantum mechanics, because that is precisely what people in certain wishy-washy and I don't know, in certain wishy-washy branches of knowledge, they wanted to get rid of anything that is definite, clear, and understandable, and just replace it with this endless layers of interpretations and cultural relativism. And I think that's unfortunate that the cultural anthropologists won, as opposed to people who want to say causal explanations. I think causal explanations are more successful, but in cultural anthropology, anything goes. And quantum mechanics was there available to say, so too, anything goes in physics. And then that's why I think physics then lost its its supremacy at some level, it just became a cocktail party topic rather than a topic that had much authority over as a role model of what other disciplines should be doing.
Well, I want to know, like, do you have a sense of what Niels Bohr's problem was?
Come on. Here's a guy who wanted to falsify conservation of energy, and he wanted to deny photons. So I think at some level he wanted to make discoveries as comparable to what Einstein had done. So there's some sort of an intellectual greed. I think he didn't have the mathematical chops to really advance quantum mechanics much, not like Schrodinger and Heisenberg did. So then that cornered him into a situation which he's basically philosophizing around this stuff. I don't know. Yeah, again, to me, it's fascinating that so much of culture is focused on acceptance. In physics, it's take the formula down and don't try to understand. In politics, it takes other shapes. And in the case of Bohr, it's just interesting that in other words, we are just faced with a group of people as if they are a pantheon of heroes who each made successful bricklaying contributions on this building in which we live and for which we should be thankful. And again, I think there's he knew how to play that. He knew how to become a hub by intellectually seducing or debating individuals until they agreed with him.
Well, he was really, really famous in Copenhagen and in Denmark in general. And
still is.
But I mean, I remember reading that there was a point where either he was getting on a trolley car or somebody else saw him on a trolley car, and the two of them, it was another physicist, and at the door of the trolley, they started talking, and a crowd gathered, and everybody was watching and just hanging on every word. And it seems like that must contribute to his desire to take hold and to keep hold of the theories, because there's a very discrete sense that you can't change the bottom line of the theory that you've been proposing. And so do you think that his fame played into his formidable opposition to any kind of changes?
It's difficult. Yeah, I don't know what to say about that. There's something that people crave, which is mystery. Bohr understood that, and Bohr wanted to give it to people. So I remember at some point somebody gave a physics talk. I don't remember right now who it was, whether it was Feynman or who it was, but Bohr was kind of annoyed that everything was so clearly explained. Like he wanted... Bohr was notorious for writing in this relatively impenetrable and long-winded format, and that's symptomatic of certain traditions within physics and math that enjoy this obscurantism. What I'm going to tell you is very, very complicated, and you're not going to be able to understand it, and so on and so forth. So I don't know. I think he played up to that, and the culture ate it up because they just love that.
Do you think it's a way of formalizing and in some sense normalizing your own lack of understanding as a physicist? You know, it seems like there's this huge cultural problem right now with people, you know, everybody from the person on the street all the way up to the politicians, leaders of the country have a really hard time saying, I don't totally understand this situation, and then soliciting more feedback. What is that?
Yeah. There's it's a widespread cultural hypocrisy. It begins partly with imposter syndrome, and sometimes it's hidden by the delusion that nobody could have understood it. You take, for example, the financial crisis, where once it was happening in 2008, 2009, countless economists said the most moronic thing, which is nobody could have predicted this. People did predict it. And they predicted it so clearly that they bet hundreds of millions of dollars that it would happen. They were betting that the stock market would collapse. And they were taking insurance on those bets to ensure that they'd get the money that they hoped to get on those bets. So bankers saw it coming, some economists saw it coming, but why is it that people like to veil things with ignorance? It's that, again, it's a kind of obscurantism. There's I don't know.
It benefits them. Like I think that if you look at somebody who's wildly famous and you look at somebody who is veiling something in ignorance with the supposition that they must know, right? Like Bohr's not walking around and being like, I don't understand it. He's like, I definitely do.
Yeah.
And that has a tremendous amount of power in it. And I see it sometimes in context of modernity with AI stuff. Like the people who are working in AI have a vested interest in convincing everybody that AI is going to do the things and is capable of doing the things that they purport that it's able to do, not yet, but maybe in some distant future, because they need the investment, they need the public belief. And so it's almost impossible to get to the bottom of what they really think, because there is this veil that passes in front of them and the public that they speak to, because it is in their deepest interest to say, look, no, this is exactly how it's going to go. I know it sounds fantastic, but I promise it's going to go this way. In the case of AI, they're getting money and they're able to spool out these companies. In the case of physics, it seems like it's just reputational heft, because this is way before the, academic industrial complex really gets kicked off.
Yeah.
It's a very Nietzschean analysis of just like a will to power.
Yeah. At some level, power always hides itself. It defends itself, but it also hides itself. So I think it's interesting. I have a quotation that many of you already know about Feynman admitting that he doesn't understand it. And that is one degree of difference from Bohr. Bohr didn't actually say, I don't understand. And you bring that out. So they set up this big mystery, which again is what bankers and investment managers will do. Well, there's a very technical, complicated investment products. In other words, give me your money, I'll take a slice of it, put it in my pocket, and good luck. And then I'll invest the rest. So yeah, I think power depends on deception. Because when Darwin goes on the voyage of the Beagle, the main reason he's there is to accompany the captain, Robert Fitzroy. Because obviously, if you just have the captain dining and lunching and having breakfast with his underlings every day for 5 years, they're going to discover he's just one of them. He's just another moron. So when you discover someone's just another moron, inevitably somebody say, how about we do this instead? And then eventually you're throwing the guy overboard. So part of the whole structure of mutiny and society involves, how do you prevent the lower people from knowing? So I think that if I could add it to the theme I brought up earlier about this medieval education being accidentally infused into modern physics, countless times a physics professor could rename or explain something more simply in order to pull students in and help retain them. Instead, they tend to do the opposite. Even Feynman's lectures, which are beautiful and impressive, mainly consist of making something complicated into something more complicated by talking about it in an indirect way. So I think again that there's an unfortunate thing happening in the distribution of knowledge that involves wrapping it in obscurity to allegedly make it sound more fascinating, but thus making it more difficult and elevating the expert as though what they're doing is something that nobody else can do.
And it seems like mathematics plays into that story heavily, right? Because it's almost, in some sense, to make that equivalence to the medieval times, it seems like in medieval times there was Latin, right? And it was, in some sense, this barrier that kept the layperson from truly participating in the theological statements going on, right? And, it's really interesting to me that the chemists of all of the scientists, maybe biologists to some extent, chemists have a very physical understanding of the universe, right? The molecules must fit together. There's actual material interactions.
Cause and effect and physical structure still exist in chemistry. That's why I was saying that physicists should teach physics while being more mindful of materials. What are we actually talking about?
Right.
What, when you talk about a polarizer, for example, what exactly is the polarizer? You have to talk about those elongated molecules.
You got to start looking at them as antennas.
Actually, right? I saw the explanation you guys gave. Very thoughtful, very interesting. But again, normally what do they do? They'll represent the polarizer as just another lens.
Well, what's the most interesting about that is that we spent so much time. So we published this explanation of the three polarizer paradox. For those of you guys that don't know,
we have another YouTube channel too. It's worth mentioning.
Yeah, so it's called Material Atomics, where we basically try to come up with material explanations for light, gravity, electricity, and magnetism. And one of the questions that we had was the three polarizer paradox, right? You have two polarizers 90 degrees to each other. It's totally black. You put a third polarizer in between them at 45 degrees, and all of a sudden it's not totally black. Like, how does that happen? And in trying to come up with a material explanation for that, we needed to understand what the structure of the polarizer was. And we realized that most of the diagrams that were on the internet were conflicting with one another about what a polarizer actually looked like, what the internal structures were. And
literally the orientation of the pillars.
The lights,
yeah, like does the light that comes...
Like textbooks that were conflicting with each other that had different orientations. It was unbelievable. Really, like high-end textbooks.
Yeah, because it's people copying people, all of them pretending that they know what they've talked about, what they're talking about, when they're just echoing somewhat.
We ended up going to an electrical engineer to actually get because they're the only ones who actually build the things, right?
How to build this.
So they actually understood the orientation of what are essentially conductive elements, which are interacting with the electromagnetic radiation. So that was just one pretty wild example of how far things get, right? Because the mathematics, you don't really need to understand that. You can still determine what the angle the angle of twist needs to be in order to get this certain amount of transmission and so forth. You can work inside of these mathematical worlds without really articulating them to physical reality. And I wonder if in the future, along with what you're saying, starting with the actual physical experiments first, starting with an actual physical representation, much like the chemists do, of the atoms interacting, would resolve much of the mysticism that's been introduced into physics.
It's a start. I think it should be there. It's hard to think about it abstractly. So to go back to the example that we're just speaking about in a moment, the nature of light is enormously mysterious. I want to write a book about light, and people do diagrams to try to represent what it is. And when they come up with certain words, like, for example, the term electric field and the term magnetic fields and then the term electromagnetic fields, when they come up with those words, they don't yet know certain things. Only decades later do they discover certain things. And then they say, aha, let's call the light particle photons. And let's say that infrared light is also made of photons. And the whole thing could have been called, this is a field of photons. But why is it that physicists feel rewarded by calling it the electromagnetic field and drawing it in these orthogonal waving paths? There's something in the drawings that isn't innocent. It isn't illustrative. There's something misleading in the drawings and false. And the reason the drawings are so successful is because other people don't try to draw whatever's happening in a different way. If nobody tries to do a different drawing, then you get the same repetition of the same thing. When we're talking about the third polarizer paradox, which is something interesting, of course, you should look videos of it, or better yet, just buy some polarizers and play with some light. When you're looking at that, the way it's taught, it's all focused on the radiation. What is it about the mystery of this radiation? What does it mean that the radiation is polarized? But you can shoot light through 3 layers of mirror of glass, transparent glass, without getting this effect of this blocking. So because you can do that without getting the blocking, then the crucial part of it is the polarizer. So there's something very unusual, and you have to get to the molecular structure of what is it that this substance is, what kinds of variations in the substance will make or will not make light do this. Why is it that you can get polarized light that is reflected off of a puddle or off of a mirror? Why is it that in other words, there's a material process to the physics that is normally neglected if you just draw substances like, I say, here's a line, and let's call it the refractive media. Rather than see, what are you talking about? Are you talking about water? Are you talking about glass? Are you talking about crystal? Some crystals are anisotropic, others are isotropic. You have to tell me what you're talking about. And why do you say an anisotropic crystal? Tell me what it is so I can go get one. So there's this endless hiding of the materiality of the physics that is frustrating. And I think it should be frustrating because we should begin from the materiality to then get to the generalizations.
I wonder if that doesn't come down to the fact that the whole idea of atoms was so controversial up until maybe 120 years ago, where there was just a real, I don't want to say dismissal, but ambiguity about their existence.
Yes, they didn't want them. So I started to try to say this in my talk, and it's totally lost the thread of it. What I want to say is there's a typical way of teaching quantum mechanics, which is that it begins with the quantum of energy, Max Planck, in the year 1900. I think that's very strange. I think when somebody rewrites the history of quantum mechanics, they should rewrite it as the history of the quantization of everything. And then they should say, well, look, people thought ancient atomists were borons, and they thought it for hundreds of years until finally, by the early, middle 19th century, they start to acknowledge, matter kind of is made of these little lump particles called atoms. They might be further divisible, but it is made of these little lumps. It's not just that if you touch a metal sculpture and you keep touching the toes of the metal sculpture, eventually the toe wears down. Things really are made of these tiny little bits that we can't see individually. After they do that, then they quantize gases. Say, oh my God, gases. Statistical theory of thermodynamics. And then considerations in statistics of thermodynamics, and accompanied by a series of denials by Max Planck, lead Max Planck, because Max Planck wanted Boltzmann to be wrong and entropy to be correct. But he kept finding that the equations were reversible, that he could not ground Maxwell's equations in entropy. He just couldn't do it. And then begrudgingly, Max Planck comes up with a quantum of energy. And then you have the quantum of light. And then you have, and I skipped the quantum of electricity. So we go, matter is quantized, gases are quantized, electricity is quantized, heat and energy are quantized, and then you go, light is quantized, and then you start finding more in invisible particles that you couldn't find. So there's this, and then we associate that with the name quantum mechanics. But ironically, throughout all that time, what the physicists are trying to do is get rid of the quantum. That's it. And they'll tell you time and again now, well, we have found it's actually all waves. It's all waves. Bob Wald, all countless physicists, quantum field theory, that's what they claim. Well, particles are just tiny momentary solutions they're in a wave field. They're really all waves. It's very interesting to me. I think there's a phobia that is a long-lasting dread of materialism, atomism, and at some level, atheism. Because at some level, these people, they were worried that if everything is just made of little billiard balls bouncing around, then they wouldn't have the things they want, like the ability to see your dad after you die, and also the ability to live forever, and the other things of the ability to, talk to dead people. There's all kinds. The ability to someday talk to the all-powerful creator of the universe. So atomism got a bad rap because it was embraced by atheists. And because atomism was kind of associated with the atheists, then even physicists were dying. How do we get rid of this thing? So to this day, I think much of that alleged duality between wave and particle, to physicists, many physicists have been solved, and it's all fields. And I think they're wrong. I sympathize with the particles, as you may have seen, but I also think that if you're working with experiments, whether it's with photomultipliers or with photographic plates or whatever you're working with at a subatomic level, you're kind of stuck with those. It kind of leads you towards the particle picture. And then the more you go to the math, the easier you get to the waves. So when you're dealing with the experiment, you get these lumps.
And it brings to mind a word that I think I'll probably come back to many times this weekend, which is reification. And when I think of the word particle, for a chemist, it makes a lot of sense. You have a particle of dust, you have a particle, maybe a molecule, or even an atom. But for a physicist, some of these fundamental physicists, a particle is a dynamic entity. It's more like an event, actually. If you look at something that has inherent intrinsic momentum, let's say.
It's not this dead inert block of stone.
It's not a static concept, right? It's not something that can be conceived of statically. It's in motion already. So you'd make this mistake, and in philosophy it's called the fallacy of reification, where you treat a dynamic entity, some event or an occurrence, as if it is a static actor, and then you start moving it around. It's sort of like if you take an abstraction like happiness, and I try to hand you some happiness, it doesn't really make sense. But we get away with it in physics for some reason. Mm-hmm. And I wonder how much confusion can be rooted back to the fact that the physicist's concept of a particle is not the same as the everyday person's concept of a chunk of material.
Yeah. And I don't know what to do with that, because then there's also quarks that can be more massive than a proton that they are composing. So there are the word particle in particle physics is overstretched, and then there are these particles that exist for a millionth of a second, and yet we're supposed to believe that it really did exist. That really is a particle, rather than calling it an effect or an interaction.
Or an event.
Or an event. Yeah. It was an event instead. No, we want to call it a particle. That way we discovered that particle. So there's what is the name of this woman on YouTube? Is it Sabine Hessenfelder?
Hessenfelder.
Yeah, so she complains that physics became a machine for creating particles. Everybody wants to discover particles, and whatever they find, they call it a new particle. So it's strange that these traditions coexist. On the one hand, the urge to find new particles and say, give me more money. They want the government to give money so they can find a new particle. And on the other hand, the physicists are trying to eliminate the particles by saying it's all waves.
And I guess the problem is that it's interminate, right? If you try to talk to me about building something out of happiness or any abstraction, right? Or busyness or any event, right? Or a conference, let's build a house out of a conference. It doesn't compute. You can't actually build physical structures out of abstractions purely. And so it seems like it's, in some sense, no matter how many of these standardized events that we keep discovering, new particles with these colliders, there's still events, and trying to construct a physical landscape out of events seems like a doomed task to me.
Trying to convert a physical landscape out of events seems what?
It just seems like a doomed enterprise, like trying to build physical structures, to build an atom out of events seems like a very dangerous task in the first place to me.
What's the alternative?
The alternative would be hypothetical material, like to build an atom, essentially, to imagine a structure for the atom that's capable of giving the events, right? Giving those dynamic measurements. What is the atom doing, or what are certain structures of the atom doing in order to give us the event called the electron, in order to give us the event called the proton, in order to give us the event called the quark, or called, the photon, or any of these things, right?
Yeah.
And that comes from a departure from materialism. Like, I think the materialism at some point became very unfashionable. And I don't totally understand that transition. And I think we spoke when we had you on the podcast about the Enlightenment as the moment where these two things broke apart from each other. Because on one hand, you have Descartes and you have the Cartesian vortices, and everything emerges from the enmeshment of surfaces. And Descartes is very, very focused on the idea that there is a substance that is forcing these things to move. And Newton comes around and he's like, hey, that math doesn't work out. I can't come up with the math for it, but this is what I have. And so I feel like all along the way we've been...
And Newton says it doesn't matter too. He says we don't actually need those. It's not even the job of the experimental philosopher to come up with these sort of things.
Yet, that's the crazy thing, is that Newton in the Principia is like, hypothesis non fingo. I have no explanation for gravity yet, because we need to collect a lot more data before we can start to figure out what exactly this thing is. And I feel like the spirit was that one day we would come back to a materialist perspective. But physics suffers from illegibility. Like
what?
Illegibility. Like biology, you can look through a microscope and you can see a cell and you can stain it and you can see the chromosomes moving apart and they're doing something and the cell wriggles under the microscope. And so you can make these theories about what something is doing because you can see it. But this kind of comes back to your question about the detectors and the engineering, which is that if you're building a detector that lets you see something, at the end of the day, you're not actually looking at the thing in itself. You're looking at the effect of the detector, and then you have to reconstruct moving backwards. Okay, we see this interference pattern, and the interference pattern is an indirect readout of the behavior of the electron, and the electron is this strange, perplexing thing that interferes in a way that we don't understand. And because we can't see it, we assume that it is beyond the ability to actually grasp. And I think that that's the largest question. Is it beyond our ability to grasp, truly, or is it simply a limitation of theories 100 years ago not having the kind of material science that we have now? And what really needs to come as we move forward is a return to a form of physical materialism. And I know that Shiloh hates this because people accuse him of being a materialist all the time.
It comes with spiritual valence that I don't enjoy.
Sure. Yeah. To jump in right there, I do think the word materialism has been ruined, and I don't mean.
Why do you think it's been ruined?
To revive it. Well, I don't know. Dialectical materialism. There's
outside my pay grade. What is
I'm
that?
sorry?
I said outside my pay grade.
Well,
if
someone says I'm a materialist, it sounds like I have a lot of Porsches in my garage or something. What? Porsches, or I collect a lot of materials. It makes me think of that. It has that valence to it where, the truth is I own very little, but I do think that physics of all of the sciences owes material explanations to reality.
Yeah.
Leave the psychologists and the mythologists to the compounded mystic interpretations.
But why do you think that dialectical materialism was what gave materialism a bad name?
No, not necessarily. What I'm saying is just that materialism is an old ism. So any intention to talk about physics by focusing on materials and then to call that an ism is dangerous. You're endangering the project by giving it a label that already. For example, a materialist sounds like, oh, you're someone who doesn't believe in spiritualism. You're trying to deny experiences that I've had. And, I've had personal relationship with God, and you're trying to take that away from me. Why? Just because instead of saying material, you said materialism. Yeah. So there's, or it might sound that it's got to do with capitalism, that you're talking that there's a certain greediness in it, that you don't believe in ethics and principles, but in accumulating wealth, or something having to do with Marxism. So there's, there are words that suffer too much. You take a guy like Bernie Sanders, I think he would have had far more success in politics if he didn't just didn't call himself a socialist. Bernie, what is it that you want to do? Just don't call yourself a socialist. You'll get some more votes. But I say, look, Bernie, and I like Bernie. He was my favorite. But I'm like, look, Bernie, people remember that in the 20th century, there were these Soviet socialist republics. And they remembered that there were these national socialists called Nazis. And now you say you're a socialist? Why do you have to use that label? Yeah, because there are some other socialists that I like who are the good ones. Anyway, so what I'm getting at is these words are some of these words are loaded, some of them are tiresome. What's important is to focus on what is it that is actually happening in the physics, so that the physics can make some progress that has to do with illustrations and diagrams and changes in the system. I was talking a moment ago about the conflict between waves and particles, and I remembered that I had written this phrase that I wanted to read, which is, there's something repulsive in atomism. In other words, in the quantum, in the idea that something is a little lump somewhere. It's just annoying. The human mind prefers to think that it's spread out continuously like a differential wave equation. So I wrote, it's repulsive that anything is anywhere at a time. Like, wouldn't it be nicer to think that we're here and elsewhere too, and that we're linked to distant places? It just fills you with hope to think that we're not just at one location. Instead, what people want is everything is everywhere, or everything is in infinitely many places all the time. So maybe not everywhere, but at least, so if the electron is spreading out and it's spread out this much, it's not everywhere because it's not in Jupiter, but it is in infinitely many locations right here, and they like that. So why is it? I think there's something both in mathematics and in physics whereby the infinite, whether it's in space or in location or in a recurrence, is soothing. In other words, these are people who had moved away. Oftentimes, people who are physicists had moved away from certain things in the religious trajectory of the Western society. And they were spending more time in the lab than in church, more time doing experiments than in catechism. And yet, what do they crave? They crave infinity. They love it. They love writing dx dt. They love thinking that it's infinitesimally small. It's not just two squiggles of ink in writing that they really have written something that is infinitely small. And it's weird. Why is that? It's like the human spirit craves this mystery that is everywhere.
Well, Nietzsche kind of predicted that this would happen in some sense, right? As we became increasingly technological, we would have to put our faith into something, right? And I feel like the physicists, as people have moved away from traditional religions for whatever reason, they're still quite popular, but I would say at least in the developed Western world, people move away. They have to still go to someone for answers. And for whatever reason, and I think it has to do with physics being the king of the academy,
or having been, it's not anymore. I mean, for example, here at UTAustin, the physics building is relatively humble and it's abandoned slightly, while say engineering is doing really well, and the law school is doing really well, but physics is just kind of a little bit of an embarrassing. And physicists feel it. They're like, here I'm in my schleppy office. Why don't they respect and admire me anymore? I say it's because of Bohr. Bohr did this. Well, Bohr did this to you.
There's a huge brain drain too, from what I understand. Like my friends in the physics department when I was in grad
Finance,
school,
business.
Yeah, they all went and worked on Wall Street afterwards, or they went to work for Palantir or somebody who's going to pay them, right? I think that any PhD student who's staring down the barrel of an academic career at this point has got to be scratching their head about, is this really what the best use of my life is going to be?
Wouldn't it be fun to be at a university, relatively small one, when, how colleges get shrunk once in a while and every now and then they relocate people to the wrong department or the wrong schools? Imagine being a physicist suddenly being told, you will now be in the College of Arts and Sciences or something, or you're now going to be part of the humanities. I don't want to be here. I don't want to be here because what I'm doing is really good and these people are just doing bullshit.
And concrete.
My physics department at my university just got swallowed by the business school. Actually,
it did. There's one.
So our physics department is now in the business school.
Hey, you guys kind of do some math. That's kind of applied physics. Why don't you just you're going to provide physicists to the finance sector anyway. Might as well.
Actually, our department chair also resigned and went to work for the actuary industries.
That's great.
That's how it goes.
And coding.
So we have some questions that we didn't get to from the live chat, and I wonder did you have something else that you wanted to ask?
Yeah, let's take some live stream questions.
Okay, so somebody, Ivan was asking, when you were presenting, you talked a lot about Bohr and Heisenberg, but the question is, were there other figures that were influencing their ideological approach to physics and then pushing it really hard, or were these two figures enough to set the stage, so to speak?
Wolfgang Pauli really was influential in shutting down some conversations and just enabling formalism to be what matters. So long as you can do the equations, that's all that matters. Anything else, you're wasting your time. Because think of, Pauli would fit nicely among modern physicists, but Bohr and Heisenberg would be looked at as weirdos because they're people who cared about philosophy extensively. Pauli had some interest in Jung and in certain aspects of learning, but he wasn't mixing that stuff into his physics the way Heisenberg and Bohr did. I think Pauli set the tone of this hard-nosed. It's almost like a handbook engineer. It's a strange thing to say. I don't. There are some engineers here present, but what I mean is, at some level, physicists who should have been in investigating the nature of things became people who instead apply a rule book and they presuppose the rules are correct, like a handbook engineer. And so, in other words, not a real engineer who's really trying to divide. Well, I've got my book. I'm going to apply this, and there I've solved the blah blah blah. You apply the equations, you get the solution. As Thomas Kuhn would have said, from author of Structure of Scientific Revolutions, you apply the paradigm, you apply the tools of the paradigm to the next problem, assuming that it should be solvable, you get the expected solution. In that sense, I don't know. Yeah, I would put some of that on Wolfgang Pauli. But again, I don't think the blame game is fun. Much of my time in history of physics has been invested studying Einstein. So Einstein is very different from this. And the way Einstein explained it, he said that history should teach people the history of individuals. And what he meant by individuals is you should find out how one person dared to oppose something and do something new. Every now and then, individuals are able to do something. So you can create independent thinkers who can disagree with one another. And of course, Einstein didn't win, but Einstein said, if I could be afforded the level of independence that one gets now in physics education, I would prefer to be a plumber. Why? Because again, these people are just not being allowed to think. And I think when we discussed it in the podcast, the way I said it was that as a physics student, you're not being encouraged to hypothesize anything. Just look, this is the way things are. Learn them. If you can take that, then maybe you can do your master's and your PhD, during which you also have to learn how they are. And then you do your postdoc, you have to learn how they are. And maybe by the time you get to be a physicist, you get to think and come up with your own theory. But by then, maybe not. Maybe then you're a team of 450 physicists where you're all working on the same thing. So there's something, part of the unfortunate thing would be that these kind of paradigmatic group thought, the group think takes over. And it's partly when you're going against the group think that you get someone really angry. Because they want to say that none of us, we're the members of this thing and you're not a member and you're not saying what we're all saying, therefore you're wrong. So that psychological reaction is unfair and unfortunate, because the one place where you shouldn't find it is in a place like physics. In physics, they should be relaxed. They should welcome debate on hypotheses, and they should be happy to help you give birth to something new. But that's not how it works.
I mean, there's a lot of money in it. If you look at the funding for physics, there's more funding for physics than there is for any of the other sciences, and that's a zero-sum game.
Even medical.
I think so. I mean, particle colliders are more expensive than cancer research, as far as I can tell. For better or for worse. And so Ivan actually had a really interesting follow-up question to this, which is how to deal with the constant irritation of confronting these limitations. Because I feel like it can be very easy to become embittered, right? You have ideas, you want to share them with people, you want to be able to have discussions about other ways that things work, you get shut down. Is it possible to stay in the space and not be embittered? And if it is, what is the path to that? Do you just have to study history?
I don't know. It's a great question. There have to be places where people are optimistic and welcoming. I don't know what to say to that. My instant reaction was to say, ask women physicists, because maybe they've had to somehow survive in a world of physics and the traditionally male physics culture, which is a particular way of being. I don't know. I think it's interesting that now because of the internet, also there's been journals for quite a while. Somebody just mentioned to me there was a journal called Galilean Electrodynamics. I don't know if it's still running, but there are several spaces. I remember one was called Physics Essays, where people who are relative outsiders get to publish things and still publish them with a certain rigor and engage other people that are peers or that are peers at least at their level. So I think there's some hope in alternative spaces leading to more hypothetical and more alternative physics. In other words, I think it's a good time to be alive. And, I think it's not like there's really a rock solid evil orthodoxy in physics trying to hold everyone down. I think physics education, however, is very repetitive, it's very orthodox, and it's very it's so packed with stuff that there's not a lot of room, there's not a lot of time for thinking. And I think that's the problem. You've got to create some courses and some spaces which people can just talk informally and critically. Look at this. Hey, kids, hopefully this is wrong. Let's see if any of us can falsify Heisenberg's uncertainty principle. Put it that way. I tell my students, yeah, you falsify Heisenberg's uncertainty principle, you're on the cover of Time magazine or on anything. You will be, this is it for you the rest of your life. Kind of associate these things being wrong with some sort of a success. Every now and then somebody just comes on and says, yeah, maybe the speed of light is not constant. And when they're a famous physicist and they say it, then everyone's like, okay, maybe it isn't. But when it's an outsider, they're like, oh my God, you crazy jerk. So it's why is it that when the famous physicist says it, people are so comfortable with it? Or the famous cosmologist, well, that galaxy is moving away at such a speed, that's faster than the speed of light. When they talk that way, it's so I think there are psychological things in the discipline of physics that are unfortunate, but so it happens with all disciplines. They tend to exclude.
One thing that I could see a space for in the future, and this is something I'm going to try out in my astronomy course next year, is hypothesis generation. That's a muscle that you have to develop, right? And I don't see a lot of that in intro science or basic science courses at the university. And when I inherited this course, there was none of it. And, in terms of planetary science, just kind of going, outside of what we're talking about here, and there's been so much new data coming in from all these telescopes, and most of the explanations we came up for the evolution of our solar system were based only on our solar system for 300 years. And now that we see all of these other solar systems developing, the field is changing really rapidly. I think it's one of the fastest moving sciences, and it seems like it's a great opportunity for kids to develop new theories for different formations, right? Because it's a wide open discipline with tons of new data.
Yeah.
And I would love to see more science classes bringing in that element of, you don't have to be right. I don't expect your hypothesis to be right, but how could you explain this if your hypothesis was right? And then maybe give me some idea of how you might go forth and track down whether it was right or not. That would be really cool to see.
Yeah, it would be interesting if historically there were a series of examples showing how people coming up with hypotheses led to progress. To just teach people hypotheses are a good thing. It becomes gross if you're just inventing them. Everything that you want to explain, instead you explain it away with a non-falsifiable hypothesis or with a hypothesis that is a word. For example, why is this light doing what it's doing? Because it's polarized. Why is this material behaving the way it's behaving? Because it's a polarizer. Why is this phenomenon happening? Because it is polarization. These things, none of these words are telling me anything. This is just ridiculous. It's just something ridiculous that happens in physics until you can have the picture, or at least the experiment showing you what we're talking about. It's just a ridiculous thing to start putting words on things. So I think, pedagogically, there's a lot that can be done, and that's kind of exciting to think that it's like wide open. Anybody can come in, and you can also fix it historically. Like most of the history that shows up in textbooks is just wrong because people, they'll say, oh, in 1897, J.J. Thomson discovered the electron. Why? Why do they say that? Because it's a way to disguise your ignorance. The truth is, you don't know how the electron was discovered. So the easiest way is to say a person did it and give a date. This is when, JJ is walking around the woods and he finds the electron. Aha, we found one. People have been writing about this stuff for over 10 years. They've been doing things like deflecting them, and they had been saying these particles of electricity impart momentum, and they are smaller than atoms. So they had been writing about it. Instead, the textbook will say the wrong thing. So it's interesting. Why are things missaid? Who did what? That's missaid again and again. And even say the Lorentz transformations. Well, the Lorentz transformations already Voldemar Vogt had formulated such like equations, slightly different in terms of the numerator and the denominator. But this thing is 1887 before Lorentz. Why does nobody talk that way? Or another one is I was saying there's something about the names, but there's something also about the physics. They say, aha, once light is a certain color, red light, it's always red. Why do we know? Well, Newton did it with a prism. They're like, aha, Newton, the great genius, it'll never change. And he's like, well, why do you have to wait years or decades before you realize that actually Compton scattering, the frequency of a light does change on an interaction, so that you can say, actually, what we just taught you about Newton's theory of light is wrong. Just say it's because they don't teach you. They don't teach you some of these things. They enable them to become permanent. Some of the foundations seem rock solid. As I was saying, the principle of the constancy of speed of light. Well, Einstein abandoned it for the general theory of relativity. He's here in an accelerated reference frame. The speed of light does change. So what can you do? It varies. It's a variable. Live with it. So there's a schizophrenia here. That is how the authoritarianism remains. Because things that are not quite as valid as they're supposed to be continue to be presented as if they are rock solid and permanent, when actually they're not. They've been modified or bracketed so that they're only partly valid.
And also to maintain mysticism, like somebody mentioned in the chat, that there's a relationship between probability, mathematics, and mysticism that is woven together most obviously in the quantum world.
Yeah, we haven't talked much about probability, but yeah, I think that's when we get to the question about why quantum physics became so intriguing. It had to do with this rise of probabilistic thinking. It's a tough nut to crack because it's a weird kind of probability. It's not just the claim that we're describing 500 processes and then making a summary of how those 500 processes transpired, but we're actually talking about individual events being fundamentally non-deterministic. So it's almost weird that it's called probability when a probability is a good word to describe the summary of events rather than this indeterminacy that is the abandonment of causality. That is what really thrills them. And again, I don't mind. Bear in mind, if there are miracles, I think that's better. If I get to see my dad after I die, that's better. I hope God exists. That's better. So I'm not against religion. I'm not against many beliefs. So if somebody could prove to me that in a two-slit experiment somehow the electron really has interfered with itself, I'd be like, okay, I just haven't seen that proof. In other words, what I see is different. What I see is they're trying to convince me that the electron interfered with itself because there's nothing else in there. But then my reply would be, yes, there is. There's electromagnetic fields and all kinds of other stuff in there. So it's not just one electron floating by itself in the emptiness of dark space. So I think I don't know. At some level, what we want is intellectual freedom. Let people have the willing to think the way they think and have conversations in which agreements don't have to be predetermined by whether or not Bohr, Heisenberg, and Pauli approved it.
Yeah, go ahead.
No, go ahead.
I just think that there's an element there of putting the cart ahead of the horse, right? And we're trying to understand these interference patterns or these very complex phenomena without actually stopping and saying, in a single photon between two atoms, what is actually going on there? What is changing about the atoms? How are they inflicting that change? And maybe if we were capable of stepping it back, we would be able to untangle the phase relationship so that we actually could make sense of it. But it seems like there's no room to go back to the foundations. It's very difficult. I mean, you have especially with the topics we're going to be dealing with this afternoon, there's Nobel Prizes given for some of this stuff, right? How do you change your mind about something that you've literally had a king, knighting people essentially over these findings? How do you walk back on something that's been so concretized and ordained?
Yeah, I don't know. I think it's fine. And then people can receive prizes and feel good about themselves. I think that's all fine. I like Feynman's attitude that prizes shouldn't matter much. The reward is figuring it out.
How do you walk back on something like that?
Look. I'll give you one specific example with the with the story of waves. We have you look at a book, a physics textbook, and they'll say, well, look, there are these kinds of waves, and they'll show you something that's kind of like a jump rope. And then they'll say, and here's another kind of wave, and maybe they'll describe a sound wave. And here's another kind of wave, a water wave interfering with another water wave, obviously is something different. Interfering water waves are different than a single jump rope. So you get a sense of these different water waves, and they give them names. But soon after they do that, then they just have these abstract diagrams. So after giving you a couple of simple models, they have the abstract diagrams. And now they tell you, but these are not particles. Nothing is moving. For example, from here to there, nothing is moving. It's just the wave is moving. So what I'm saying, in order for you to pedagogically do this better, you should tell people, look, whatever the jump rope is doing, the jump rope is made of atoms. It's just made of particles. So don't tell me later that the wave cannot be made by particles, because the jump rope is made of particles. The water wave is made of particles too. So I've never seen an explanation exactly how are water molecules interacting with each other to create the interference pattern, because that's what they're doing. It's just a bunch of water molecules all kind of linked together by some viscosity and God knows what. And they created the interference pattern. And the sound wave, the stuff between you and me, it's particles too. It's just some oxygen and nitrogen and a bunch of other stuff, carbon dioxide, molecules bouncing around. So the fact that you can hear me and that sound is a wave phenomena is completely 100% compatible with particles. Because that's what's happening right now. So, but they don't teach it that way. No. They make it look like there's this fundamental incompatibility between wave picture and particle pictures. And how quickly they jump to that level of abstraction without reminding the reader. Actually, every one of the three particle wave models that we described you in each of the contexts, whether it's acoustics or water or whatever, it's just a bunch of particle interactions that are too complicated for us to care enough to analyze it because we're lazy. So just explain to me how the water waves are happening. And then after we've done that, then maybe we can go back to looking at some interference, two-slit, or diffraction gratings to understand that stuff. But they don't do it that way because, again, it's just particles are gross. They'd rather have something spreading out uniformly over time, smoothly, which then leads to the problem of the wave collapse. Originally it used to be that physicists actually believed that if we emit a single electron and don't watch it, a few hours from now, that electron might be as far away as Jupiter. That one electron. So now that electron that we emitted from an electron gun might now be at the orbit of Jupiter and everywhere in between. So this is a spread out thing, the electron. The subatomic particle is now larger than planet Earth. And they loved it. They loved it because they like everything being everywhere all the time. Every particle you've ever seen, it has a wave associated with, and they're all kind of overlapping somehow without the strange. And then the moment you measure the electron, you find, there it is. It's right here. So all of that smear that was all across the solar system has now collapsed instantly. Instantly. All of that energy or whatever it was, that potential, whatever the hell it was, that electricity that was smeared over everything is now vanished. And then they said, well, let's call that the projection postulate, the collapse of the wave function. The thing is just. But now they come up with decoherence. They say, okay, before we measured it, it interacted with something else. Okay, thank God, sis. It interacted with something else in the air right here. Then the wave collapsed. So now you don't have to worry about that big wave. It's a little wave. It's the same wave. It's only that this one is only 1 millimeter big, while the other one is the diameter of the distance from here to Jupiter. Why is the little one less unpleasant than the big one? They should both be unpleasant, but no, I think they like both. There's something that's spreading that is just very rewarding. Why? Because it matches the mathematics of differential equations. That's all. They like matter. They like stuff to be infinitely divisible, because why not? I can do it in math. And so there's an aesthetic appeal to that I think is in conflict with common sense and with what we learn from interacting with objects, which is this glass is here, it's not over there. This can, it's here, it's not over there. And I'm not offended by that. None of you should be offended that the can is here. And you're like, no, maybe it's over there because you can see it too. Therefore, it's in your mind and it's all subjective. And the can wouldn't exist if you're not looking at it. And then Einstein at one point turns to Heisenberg and he says, do you really believe that the moon is not there when you're not looking at it? So you see, very soon you devolve into this, just the desire to have the electrons spread out very quickly devolves, I think, into a weird subjectivism. Anyhow.
I mean, I think that this is a topic that we will never stop returning to. And I think that it is deeply a part of physics, because understanding how all of these theories come together and the people who popularize them and the effect that it has on not just our psyches, because I think that everybody in this room sort of recognizes that these systems have gone off the rails over the course of the last century or so. But I think that there's plenty of people out in the world that are still just awakening into it. And I think that your work is really helping people delve into that, because your books are beautifully written and on subjects that really strike at the heart of what's going on here. It's the blending of mathematics and mysticism and the cult of personality. And I want to say thank you.
Thank you. I really appreciate it. And thank you, Shiloh. I think the important thing about these things should be they should be fun. You know, the world is a beautiful place, and the physics should be it should be attractive and intriguing. These, you know, right now we've just talked about a few words like polarization and electromagnetic waves, but seeing the phenomena is so fascinating and intriguing that then that's what leads to the math. But it should also lead to discussions rather than the feeling that it's all been done by people 10 times smarter than all of us.
Amen.
Right on.
That's beautiful.
All right.
Thank you so much.